Good afternoon, dear participants. Can you hear me?
Yes, hello.
Yes.
Yes.
Can you hear me?
Yes.
I cannot.
Hello.
Okay.
Hello.
Yes, now I can. Let's start our meeting today from disclosing a number of participants. First, Kirill Kalmutskiy with his thesis. Kirill,
Yes, I'm ready.
you ready? Said Mohammed Sajadi. Coursework. Said Mohammed, not present now. Oladotun Aluko. Not. Watana,
Yes, I'm ready.
you ready? And Mark Balshenko, you here?
Yeah, I'm here.
So let's start from first speaker, Kirill Kalmutskiy, please.
Yeah, one moment. I need to.
What? Kirill? Disappeared.
Okay, can you hear me?
Yes.
Sorry, I had problems with Zoom. Do you see my screen?
Yes.
Yes. Okay, let's start. My name is Kalmutskiy Kirill, and my scientific advisor is Vladimir Berikov. My topic is training of deep neural networks with incomplete training information on an example of recognition of tomographic images. So let's start from the formulation of the problem. We have a large data set of tomographic images of the brain slices, but the problem is that we have not so much labeled data, because labeling of such data is very expensive, and since only a highly qualified specialist can do this, and we want to create a support decision system which will predict areas of stroke and select them on tomographic images, and also classify them and notify doctor that in the image some area of stroke is presented. As I mentioned, we have many problems with this task, because we have very little labeled data. We have only 34 images, which is not enough to train classical deep convolutional neural networks. Also, we need to achieve not only high segmentation quality, but also high classification quality, because we want to create a decision support system, and we shouldn't make many mistakes in classification. We don't need, we shouldn't have high false positive ratio and also true negative ratio, and we need to minimize them. And also our model should be interpretable because doctors should understand decision of model, because otherwise they won't trust it, and because they won't understand how it works. And also the scientific novelty is that, as I mentioned, all current solutions require a huge amount of training data, but we have only 34 images, and we need to somehow expand our data set to train a huge model. And also we need to somehow interpret the results of our model. So the initial data was in DICOM format. We transform it in JPG format. We extract masks, then we fulfill those masks, those contours, and we also resize our raw images, and therefore we get some masks and also raw image related to this mask. The segmentation, we have many types of segmentation. We have automatic segmentation, which is not good in medical recognition tasks because they provide bad accuracy, and we can't use them. We also have semi-automatic segmentation. It is useless in such problems because we anyway need to somehow mark up our data, and also with those methods we achieve a not very good accuracy. And the most promising approach is trainable segmentation. Trainable segmentation is a segmentation with using complex models such as convolutional neural networks, and classic model in trainable segmentation is UNet, as you should already know. The UNet is a model consists of encoder and decoder. First, we transform our initial image into low dimensional space, and then we reconstruct our image from this low dimensional space to get masks or predictions for this image. But the problem is that we don't have many training objects to train such big model. Classic UNet consists of many blocks with many millions of parameters, and 34 images are not enough to train such complex model. We also can't use transfer learning for our task because transfer learning doesn't work well in medical image recognition tasks, because you can't train a network on, for example, ImageNet, and then use this knowledge for medical image recognition, because it makes no sense. And also another problem is that we can't interpret this model. So let's try to resolve those problems. First, how to expand dataset. The most common approach is to use augmentations, but in our task, not so much augmentations are useful. So we used only horizontal and vertical flips, and also we used small zoom to expand our data set. I also tried another augmentation, but they didn't increase accuracy of model, so I dropped them. You may say that why I didn't use random crop, and the reason that I didn't use random crop is that we used another technique which calls, I would say, cutting the image into sub-images, or puzzle cropping, or any other name that you prefer. But the idea is very simple. we just cut our initial image into some smaller sub images by uniform grid. And for example, we used in our task a 4x4 grid to obtain 16 images from initial images. And we use those sub images to train our model. By this simple technique, we expand our data set by, as I said, 16 times, which is very good. And with augmentations, we can increase the number of training objects by 100 times. So let's talk about network architecture. As I mentioned, we used some unit-like model, which consists of encoder and decoder, but we also add one small network we join another small network to encoder layer, which is called classifier layer. This classifier model is just few very simple layers, linear layers with ReLU and dropout. Why we use dropout, I will say later. And we train those two networks, segmentator and classifier, by using joint training. We train them with the sum of losses. The classifier tries to predict either stroke on the sub image or not, and segmentator tries to segmentate the stroke on the image. Why do we want to use two models instead of one? As I said, we need a decision support system. So we need to decrease the number of false positive. We need to decrease false positive rate because we don't want to notify doctor. We don't want to say that there is a stroke when it is actually not. And if we will use only segmentator, we will always say that there is a stroke on the image, and doctor will say that, okay, this model always says that there is a stroke, and we don't want to use it. So to resolve this problem, we use classifier layer and train this model on sum of losses of classifier and segmentator. So, and the most important part is model prediction processing. To increase the quality of model, we use TTA. TTA is a test time augmentations. So the idea is simple too. We use augmentations not only during train time, but also during test time. When we try to predict something for some image, we first make some augmentations for this image, obtain predictions for all images, for augmented images, and for initial images, and then we average all the predictions for those image and get the final prediction for those set of images. And also, to increase the quality of segmentation, we leave only one maximum connected component in the resulting segmented image. We can do this due to the fact that there is always, not always, but in many cases, there is only one area of stroke. Sometimes it could be two, but if there is one, the doctor will check the image manually anyway, and he will find the second center of stroke too. So, but by using this technique, we can decrease the number of false positive predictions. and increase the quality of segmentation. And also we can remove this component if the area of this component is less than a certain size. By this technique, we can decrease false positive rate also, which is very good, not only for segmentation, but also for classification task. So here is the result of experiments. We used two metrics. First is accuracy of classifier, and the second is intersection over union of segmentator. So we also used some technique to increase number of validation images. So we used incomplete k-fold. So we first train on we first leave 4 images for validation, train model, then we get another 4 images for validation, train another model, and then averaging results. So by this technique, we can increase the number of validation set by 2 times without decreasing number of training examples. And we also left 6 images for test to test our model. The results is on the screen. As we can see, we can achieve good segmentation results, and also not so good, but I would say okay results for accuracy. So as I said, why we used dropout for classifier, we did this because classifier tends to overfit to very strong overfit on the training data, and dropout helped us to decrease the problem of overfitting. So also I didn't say that we did segmentation only if classifier says that there is a stroke, and if classifier says that there is a stroke, but segmentator can find pixel with a stroke, we just decrease the value of threshold, while segmentator won't find any corrupted pixel. So I also compared proposed algorithm with baseline. As a baseline, I just picked UNet. I used the same augmentations for UNet, except of cropping into puzzle. So here is the result. As I said, UNet cannot be used as a decision support algorithm due to the fact that it has very high false positive ratio. So how I calculated false positive ratio, I just found 5 images without any area of stroke, and I fed them to both models. And UNet says that on those images it found some stroke, but our algorithm found stroke only in 1 image, and we decrease false positive ratio from 1 to 0.2, which is very good. And our algorithm can be used as a support decision system, while simple UNet without any post-processing and without classifier layer cannot be. So as a conclusion, I want to say that by using various techniques, we could achieve very good results on very small data set. We also were able to decrease false positive ratio and achieve good segmentation accuracy. So I said that the model should be interpretable, but so how can we achieve interpretability? We can use, instead of classifier layer, we can use some tree-based models, and which are very good in, which are very interpretable. But I tried to do this, but the problem is that those tree-based classifiers shows really bad accuracy, and with such models, I couldn't achieve good classification results, classification quality, and therefore segmentation quality was very bad also. And I'm still trying to resolve this problem. And so that's all. Thank you for attention.
Thank you. Please, questions?
Yes, I have a question. Could you please explain how did you choose the threshold when you remove the pixel? Could you please move to the slide when you say 1,200 pixel? Yes, yes. One. So I have two questions. The first one would be, how did you choose the threshold of 1,200 pixel? How did you come up with this number? And the second question is, how do you know a group of pixel is a connected segment area? I mean, what if 1,200 pixels scatter around not one small part, or it's a tip of a bigger segmentation? How do you classify it?
Why I choose this threshold? Because I tried many thresholds on validation set and also on training set. I just tried. I just found the best threshold by the grid. I tried to start from 100 pixels to I think 3,000 pixels, and 1,200 pixels was the best threshold for validation set. For test set, it was another number, but I chose validation best threshold because it is a bad practice to find best parameters on test set. So the second part, I don't think that I understood the second part of your question. Could you please repeat it?
Yes. I mean, in this, so when you choose 1,200 pixel, I mean, how do you know that part is unnecessary? What if it's 1,200 pixel is connected to a bigger group of pixel? I mean, like I see in the middle picture, you have a small dot, and in your algorithm, if it's less than 1,200 pixel, you will remove that part, right?
Yes, yes, right.
Yeah. So how do you know that? How do you know that the dot is? I mean, how do you calculate 1,200 pixel of just the dot? Because I don't know, it's just a matrix of a number. How do you know it's connected?
I have implemented a classic algorithm of finding connected components. First I found all connected components in the image. Then I leave only the biggest, the largest of them, and then I get only one component without any others, and I just sum all elements in the image, and if I get this, the sum is more than 1,200 pixels, then I leave it. Otherwise, I cut it also.
Oh, okay, I got it. I got it now. Thank you. Thank you.
Thank you for the question.
Other questions? I have several questions, starting from this slide. What is the value for your future user if you remove small connected components?
So we assume that if we left only small component, then then our segmentation algorithm is failed, because in many cases area of stroke is I would say large, and it cannot be smaller than some certain size. So by using this technique, we tries to improve to decrease false positive rates.
But by skipping small parts, you increase false negative.
Yes, it is also the problem. Mm-hmm.
And have you counted the number of images which pass your threshold with 1,200 square pixels? How many?
Yes. Mm-hmm. Yes, I also calculated that by this threshold, we don't increase the number of true negative ratio, true negative errors.
But how many images comply with this requirement? Maybe it's only one.
No, it's not only one, because yes,
in validation you have 4
yes.
images.
8 8 images.
8.
Yes, I don't know how many images pass this threshold, but I know that this threshold increase our.
Of course, it increase. It's
yes.
obvious. If you put some higher threshold, yeah, then maybe only one image pass well with your algorithm. Maybe no image.
No. I didn't remove. If we set a very high threshold, we will obtain 0 IOU for this image. So I didn't.
Yeah, it's better to check. So, and put on the 4th slide.
Of course, yes. Mm-hmm.
You said that you using 34 labeled images. What is the source of these images? What is the database used?
I used the database. I used data provided by Andrei Tulupov, I guess, from MRI Center.
Is it published source or private?
Private.
So then the question is, what is your contribution to and to which science by your master thesis?
I think my contribution in so I think the essential of my work is that we're trying to learn a model on very small data set, and I think the main contribution into deep learning. So I would say that these techniques that I used can be used also in another segmentation tasks, because they are not specific to, for example, medical recognition, not very specific to medical recognition images. And this task is just an example of how we can train deep neural networks on very small data.
It is well known. This question has a very well-known answer. Your model will overfit, definitely, because you have only 34 images, and you cannot prevent from overfitting. That's why it's very strange contribution. If you intend to contribute to to deep learning science, you need to compare your algorithm with another algorithms on some publicly available data set. So you may train on your private data set, but test on public data set. So now it's not obvious, and you have not proven that you provided some new value. And on the several next slides, please, next slide list, previous one.
This?
Yes, yes. You claim that automatic segmentation has bad accuracy. It's very strange. What is bad? 97%. Is it bad?
I tried to implement some automatic segmentation algorithms like watershed algorithm, and it shows about 0.2 maybe intersection over union.
So that's why you need to claim that your implementation has bad accuracy. But here it's claiming that the whole automatic segmentation approach has bad accuracy. It's not correct. It's not scientific actually. And in semi-automatic segmentation task, the same. So that's very strange. And you have a final table where you claim your results, nothing to compare to. Your approach, UNet, and proposed algorithm. So how you prevent from overfitting?
As I mentioned, I prevent from overfitting by using some post-processing techniques like PTA, as I said, by some knowledge about task, by removing, by leaving only one maximum component. And I also used classifier to increase quality of segmentator and to remove weaknesses of segmentator. And I also used dropout for my classifier to work better on unseen data. So I used various techniques to prevent overfitting. Of course, we can say that we beat overfit because maybe the problem is that we choose good images for test set, but it's definitely better than using existing approaches for this task.
Actually, yeah, accept this question, that answer, but again, the question is how you prevent from overfitting. Nothing special suggested by your work in working with small data set. Not actually nothing new technique proposed by your work. And the last note, you claim that your work is on training on deep neural networks with incomplete training information. How do you define incomplete information?
I guess because we don't have all patterns, I would say patterns on training set. Definitely we don't have all patterns. And we try to learn those patterns to achieve good accuracy on unseen patterns.
It's well known, you cannot define all patterns. It's
yes.
So you use the term, it's scientific work. So you need to define all the terms, but you used here the term which is not defined. And the way you are suggesting to define it by listing all the patterns. It cannot be achieved in any task. So to provide all the patterns, you need to provide infinite data. That's why it's also the question how you define because you cannot now change your topic of your master thesis. You listed in the topic some term incomplete training information.
Mhm.
You need to clearly define it in your work. What is incomplete? It may be some like strange but concrete.
Mhm.
Yeah. So now it's not clear what is incomplete. You may try to define by like some measure of. We usually say we have incomplete data if we cannot easily train on it, or we overfit, but all this not successfully, all not clear. Consult with scientific advisor.
Mhm. Okay.
Okay. Thank you for your answers.
Thank you.
And let's continue the next presentation from Oladotun, please.
Good evening, everyone. Can you see my screen?
Yes.
Great. Okay, so I'll be presenting my thesis this evening. The title of my work is Studying the Applicability of Proof of Reputation as an Alternative Consensus Mechanism for Distributed Ledger Systems. So I'll start by giving a background to distributed ledger systems and consensus in general. So a distributed ledger is essentially a data structure that is replicated over a set of network nodes, and it comprises of an ordered list of transactions that are grouped together by some certain characteristics. The important part of a distributed ledger system is the fact that cryptographic principles are employed to guarantee the ledger's integrity, which is the ability to detect data tampering. So consensus within distributed ledger systems basically refer to how the set of network nodes can agree upon some shared states or some shared data that is transferred between them over the network. So there are several crucial issues to consider when designing a consensus mechanism, and examples of which might include node failure, network latency, network partition, node behavior, out of order input, deterministic state machines, and there are several other factors, but the key one, or the very important one, is the node's behavior. And this part of distributed ledger systems has been generalized to a very popular research problem known as the Byzantine problem with distributed ledger systems. So the specific contributions of this work include the fact that in our scheme, the behavior of a node in the particular network affects its overall reputation value, which essentially translates to the node's behavior from the previous slide. Also, our approach uses a social choice function during the consensus determination. And finally, we develop an experimental implementation and evaluate its performance in terms of the consensus latency and the throughput of the overall system. So some related work, especially in line with consensus mechanisms, some other approaches that have been developed over time, first of which is the proof of work mechanism, which is by far the most popular type of consensus mechanism, although the main fight back against this has been the fact that it's a very slow approach to reaching consensus upon any shared data. Another approach that was implemented that was supposed to serve as alternative to the proof of work is the proof of stake consensus mechanism, but it as well does not provide as much of an improvement as the proof of work. So some related work that I've tried to employ the reputation-based consensus, the first of which was proposed by Yu et al. Is the reputation-based consensus mechanism that is also based on the proof of work consensus algorithm, but they essentially share the same challenges, but just some slight differences, but still the same challenges with the proof of work proof of work algorithm are still kind of surfacing with this approach. And another approach that was proposed by Guy et al. Was the reputation-based consensus for peer-to-peer networks, but they just use some agent trust mechanisms to define the reputation, which isn't exactly a scalable system. So the method we employ for generating our consensus mechanisms, I would describe it further on. So we start by assuming first that there are n nodes in a network, and then we denote an individual node as Pi, where I is an element of n. In addition to this, each node is identified by a key pair. First is the public key, and then second is the corresponding secret key. Each node during the interaction with another node can essentially be either a sender or a recipient for a particular reputation rating with respect to a service that it has rendered in the network. So we denote this interaction between two nodes. Let's arbitrarily call them I and J as this T equals a function of E, P, and R, where E to the subscript SK defines the encryption. So each transaction is usually encrypted, and what it's going to contain a reputation value and then the public key for the recipient of this particular rating. So this encryption is encrypted by the secret key of the sender, and then the public key of the recipient is added as part of the transaction inputs, and then the reputation rating, and all this information is used to generate a transaction output.
Oladotun, sorry, you providing too much information, general.
No,
Start
this
saying
is
about your work.
Yeah, this is my work. This is what I've been working on. So should I continue?
Yes.
Okay. Yeah, so this is used to generate a transaction output or a data output. So for our method to determine the consensus group, what we do is that at every stage before some data is added to the ledger, we start off by selecting a consensus group. So the consensus group is essentially responsible for determining the state of the entire ledger across the network. So at the start of each round designates the process when a new some form of data will be generated and then broadcasted to the entire network. So members of the consensus group are selected into a community, and then we denote this consensus committee by GR, and then the G really just stands for the group, and then the subscript R for a particular round. So we can have multiple rounds. So we denote that by R. So the nodes are selected in such a way that the entire reputation value for the consensus group must be equal to at least 50% of the reputation value of the entire network. So a node in this group is denoted by PK, which is also an element of GR. So this group is selected at the start of every block creation round. And then to proceed, what we do is that we take a leader from the group that has been selected from the previous step. And then after a new leader is selected, which we do by random, and the reason we do that is so that we can introduce some probabilistic dimension into our approach to solving this challenge. Its duty is to take all the data interactions for a particular round, validate those interactions. That is, it's going to check the integrity. It's going to calculate a new reputation list. It's going to sign it by its own secret key and then broadcast this data interaction package to the consensus group. So we just denote that by this formula, so to speak, or essentially it's actually a data structure by a commute. LR represents the leader that was selected, and then the block represents the set of data interactions. So what the other nodes in this network that are part of this consensus group do is that they revalidate these data interactions, and then they also revalidate the reputation ranks for all the interactions, bearing in mind that these interactions are essentially reputation ratings between nodes in the entire network. And then they also check the integrity of the broadcast through a weighted voting process. So this is where it all starts to get interesting, because this weighted voting process is based on the concept of what is called a social choice function. And we use that as the basis for decision making. So we can define this social choice function as follows. For a set of nodes in the consensus group for the current round GR, each node has an associated weight W, which is assigned to it, and it's equivalent to the reputation value from the previous round. Initially, when the system starts off, we set all the reputation values to a default reputation value that can be changed depending on the system requirements. Also, there is a minimum quota which has to be reached for decisions to be made. So what we have done is that we've set this quota to be 2/3 of the total weight in the consensus group, and then we determine the decision made by the consensus group as DG, which is a stepwise function which could either be 0 or 1, depending on if the total weights for the votes that was assigned to a particular decision is greater than the quota. The quota here is 2/3 of the total weight of the consensus group. But if this condition is not met, we just defer it to 0. So to the reputation system itself we use for our approach, we say that the nodes selected for the consensus are usually the highest ranking nodes in the network. And then we say SI should denote the reputation for a particular node I. All the nodes in the network will start with a default reputation, as I stated earlier, that is determined on the system initialization. So during node interactions, the reputation values are calculated based on a liquid rank. And then this approach can be used as a predictive metric to evaluate a node's behavior for future purposes. So the principles of the reputation system we employ are first, the liquid nature of the reputation values. And what that means is that the reputation value computed for a node is based on the reputation value of the node providing the rating. So it's going to use all the previous values that have been generated through time over the entire network. So this is kind of like a deterministic approach to reputation ratings. And then we use a temporal scoping of reputation. So what that means is that if a node receives a rating for a particular round, that rating even if it's 5, that 5 has more value than 5 that was generated from a previous round. So this is what is referred to as the temporal scoping. So to go through the steps properly, for each round, a node can receive multiple unique ratings. The emphasis here is on unique because we don't want the case where a node is receiving more than a rating for a particular round. And so the range of this rating is between 0 and 1. It's never more than 1. But depending on some system configurations, those values can be set within a particular limit. But whatever the value is set at, what we do is that we compute this rank for a particular node with respect to a set of reputation values it has received for a particular round, and then we normalize those values based on this equation. This is a standard normalization function, but what we've done is because of the fact that normalization functions generally get values like 0, but we want to prevent those null values because they don't actually add anything to our approach, and it's kind of like a challenge to work with those null values. So what we've done is that we've modified this normalization function to what we have in equation 6. So we just take a single value that was generated for a particular node. We subtract the minimum from the set for the round. We add 1 to it, and then we divide that by the maximum subtracted from the minimum, and then we had a 1 again. So specifically, we denote these node transactions as a row vector S. So when we try to compute a new reputation value, we blend these ratings with the rater reputation values from the previous round. And so we define this as P such that P is S, the row vector, multiplied by R, the row vector. So for all the sets of ratings that was generated from a round, those ratings are then multiplied by the reputation values for the rater from the initial round. So P now is the output that is now the new rank for the current round for a particular node. And then we do this for every single node in the network. So to calculate the reputation value for a particular round, what we then do is that we take, we blend the newly generated reputation value for a particular node with its own previous reputation value. And then we define that as alpha multiplied by P, which is the value that was generated from the previous step. And then we add that to alpha minus 1 multiplied by R. So alpha is a constant, which is a value between 0 and 1. And what it does is that it's essentially, depending on how this alpha value is set, if it's closer to 1, this P value essentially has more influence on the newly generated reputation value for the next round. And if alpha is closer to 0, it's generally a lesser.
Oladotun, again, you providing too much information not needed. We cannot understand, of course, what everything that you do not supposed to provide any details of your setting.
Okay.
So you provide, okay, you have done with some architecture, with 2 slides you provide detailed information about this architecture, and then what are results? Please, you always.
Okay, so I'll move on to the experiments and the results. So for our experiments, for the prototype, we built an experimental network, implemented our mechanism, and then we deployed nodes with AWS EC2 instances on a 16 gig RAM server with Amazon's T3 processor. So we implemented this entire protocol. We imposed a round trip latency of 200 milliseconds, and then we varied the node setup between 500 and 1,000 nodes. And then we added rate limiting to curtail excess bandwidth usage from the nodes. And then finally, we benchmarked the system with Apache Bench, which is an open source tool for benchmarking distributed systems like this. So these are the results of our experiments. So the metrics for the experiments are in terms of the throughput, the block size, and then the consensus latency. So for the throughput, which refers to the amount of data interactions that our system can generate or process for every single second. When the node is set up at 500 nodes, we have a throughput of about 800. And then as the nodes increase, as the size of the nodes increase, the corresponding throughput increases, which makes a lot of sense because there is more nodes that are processing the data interactions between nodes in the entire network. Also, the average block time, we vary the block size from 100 from 100 to 500. And we noticed that the average block time, which is the time it takes for a leader to produce a new block and then broadcast to the entire network, varies in a linear way, which is expected because the size of the block increases the computation time. So to recap, in a reputation-based consensus mechanism, the reputation of a node is not just calculated based on the direct ratings, but we are blending together normalized sets of ratings and corresponding reputation values. What is novel about this approach is the use of a social choice function as a means to determine the integrity of data in a consensus group. So our reputation value, our reputation system is based on two major principles, the first of which is the liquid nature, and the second is the temporal scoping. And finally, we developed an experimental implementation, and then we evaluated the performance of the system. So that is all I have.
Thanks. Questions? During the pre-defense, you will be given only 7 minutes to present your results.
I know. I
Okay,
think for this presentation, it's 25 minutes, right? For academic seminar?
20.
20. Ooh,
25 was when we were 4 on one seminar.
Oh.
So I have the first question. What is the baseline you compare to?
Yeah, so the baseline for this comparison is to compare with some other consensus mechanisms, which are the proof of work and the proof of stake. And the comparison with that is, on the average, the proof of work can do about 7 to, has a throughput of about 7 to 10 transactions per second. But for the proof of stake, there is some improvements, which is about 40 to 45.
You need to reflect on the corresponding slide. Yes, here is your result, and you need to depict baseline also to show your contribution. Now it looks like you have done something, but you every time is your scientific work. You need to compare with previous results. If you introduce new schema of consensus, then in what direction theoretically it may be better than existent, and experimentally you prove that in this direction you provided better results here. And the last question, what is about your publication?
Yes, so there is still some other sets of results I need to get as we speak now. They're still running. So once that is done, I should send it out before next week, hopefully. So I should send it out to a conference.
Okay, I see. Probably, I don't know which conference can publish in lesser than 1 month.
No, so one of them is happening next month, and I've set the deadline to Sunday, which means that all the work has to be completed before Sunday.
Okay.
Another is happening in July, and they all have the deadline for this weekend. So yeah.
Okay, I see. Thanks for answering questions. Please, our next speaker, Mohammed Sayed. Are you here? Mohammed Sayed. Not here. And then Watana, please.
Yep. How to share screen? I have not been using Zoom for a long time. I really could not find the button for sharing my screen. Oh, okay, the green one. Okay. And good evening. I'm Watana Pongsapas, and my advisor is Alexei Okunev. We are working on.
Please start sharing screen. Okay.
We are working on deep learning-based machine vision for the task of grasping chemical hardware. Regarding to my proposed thesis on previous semester, we were aiming for develop an chemical hardware detector and apply it with a scalar robot. But we faced a limitation because I came back to my hometown and I could not use the hardware in Russia. So we scaled down our thesis just to cut the part of the robot application out. And our final result is we successfully created an chemical hardware detector. Let's start. In this section, I'm talking about data set and data annotation. We use a web camera to capture 60 images of the task that was performing by a demonstrator who moved chemical hardware from place to place. We capture with a dimension of 640 by 480 pixels in landscape orientation, and we save it into BMP format without any pre-processing, such as adjustment in contrast, brightness, or data augmentation, because we want to simulate the real environment. After that, we split the data with a ratio of 80-20. So 48 will be trained images and another 12 images for testing. Then we use a label me. It is a tool for object annotations. We draw a total of 633 polygons, and you can see here. There were 7 classes of our object of interest: black rubber, empty hole, grabs, hand. And this is a grabs, hand, shaker body, and stand and tube throat with a total number of 633 objects from 48 trained images. In our training, we apply detection for solving instance segmentation because detection is an alternative to a part of TensorFlow and PyTorch. However, detection is based on PyTorch, and these two already provide over than 200 model inference code and pre-trained weight. And since our task is instance segmentation, we apply cascade max CNN. And this is the name of the module. We select this one because it has the highest average precision of 44.7. This model is based on LessNext 101. And we also applied a checkpoint for faster training. We run the model with 100 epochs with learning rate of 0.02 with a GPU Tesla V100. The training took about 20 minutes. And I skip the slide. Here is a visualization of the detector. Okay, let's get back to the model evaluation. We evaluated the model by using IOU, intersection over union. And for these 7 objects, most of them okay. We use a threshold of 0.3 for IOU. This number was suggested by my advisor, and most of them got scores over than 0.9. Only just a checker body that has the lowest score. I observed this incident manually, and I found that the test image, I mean, there are some images that the shaker body was covered by the demonstrator hands, so that we lost a lot of feature of the shaker body. To conclude, detection provides numerous model inference and pre-trained ways. So it facilitates the user, which is asked to perform tasks. And yep, we obtain great results on the most subject and the lowest score of 0.838 on shaker body. However, this problem could be improved by maybe a larger trained data set. And our contribution is obviously that our implementation works well on only our trained data set, which we created by ourselves, and it might not work well with in other implementation which has different shape or appearance of the chemical hardware. But we proved that this instance segmentation task with deep learning approach could be performed and yield satisfied result on detection. an alternative to part of TensorFlow or PyTorch. And moreover, this task, the chemical apparatus detectors, can be developed further and applied with robotic arms, like a SCARA. So in order to automate the task. And this is my work.
Questions? What is your scientific contribution? To which science you contribute?
Computer vision task.
You applied well-known technique to your data set. It's engineering work. You put together well-known components, detection, labeling. What's new?
Could you please repeat the question?
What new scientific knowledge you obtained during your master thesis work?
I think it is not that pure scientific, but we show an alternative to that can perform deep learning tasks.
What alternative?
MM detection.
MM detection.
Well known.
And what is alternative to MM detection?
I mean, MM detection is an alternative to TensorFlow or PyTorch.
It's well known. It's not your result. We know already. That was like you trying to solve automation task with the help of deep learning methods. And you need to compare with another ways of your automation task solving. Like previously, the task of grasping chemical hardware is used to be solved by OpenCV algorithms, for example. And you apply deep learning algorithm and you compare the performance from previous level to your current level. Now it looks as a work in greenfield, but you provide no scientific overview on work done in this field. Who else already have been doing grasping chemical hardware automation? Do you know?
Yeah, I have in literature review, but
yeah. So
yeah,
put one slide on overview how the task of grasping chemical hardware is usually solved, automated. Or it's not, it's your very first work is yours about automation grasping. I don't think so. So you need to provide one slide here, because without this slide, it's very, very strange, looks like bachelor work of engineering faculty, not scientific. Other questions, comments, maybe? No. Okay, thanks, Watana.
thanks.
And let's go to the next presentation. Syed Mohammed, are you here? Not here. And we come to the last presentation from Mark Bolshenko.
Yeah, I'm here. 1 second, please. Can you see my screen? Can you hear me?
Yes, we can hear you.
Actually, yes, we can hear you.
Okay, can you see my screen?
Yes, indeed.
Yes.
Thank you. Let's start. Hello, everyone. My name is Mark, and now I tell you about my bachelor's work. Text-to-speech is a technique that produces artificial speech and aims to create a natural speech for originally given text. The typical structure of the text-to-speech method consists of two parts. Prediction Mel spectrograms from a previously known text and speech generation from the obtained Mel spectrograms. In speech synthesis system, the generated Mel spectrograms are highly smooth images which affects naturals of speech. To solve this problem, it is proposed to use a CNN such as UNet to increase the resolution Mel spectrograms. Increasing can contribute to the appearance of noise in the Mel spectrogram, which will improve the naturals of speech. At the moment, there is one work on a similar topic to improve speech quality, that is pre-processing Mel spectrograms before the vocoder to improve the naturalness of speech. This is the work of NSU master's student, Sheng Lin, which is called generating high quality synthetic speech using GAN as vocoder post-processing. As you can see from the name, from the title, it uses GAN to achieve its goal, and its development is showing good results. Predicted score predicted score equal original. To achieve our goal, task was set is implement super resolution pre-processing Mel spectrograms, train super resolution pre-processing, implement research pipeline, and analyze the received metrics. Now I tell you about how I create dataset for super resolution network. Alger speech was taken as a basis, and after this torch transforms Mel spectrograms, we get the target part of the dataset. It is a lower arrow on the screen, which target part contains the spectrograms of the original sound with a high resolution. After we apply Griffin-Lim algorithm and get audio from original Mel spectrogram, and after we get Mel spectrogram bad audio signal, because Griffin Lim involuntarily degrades the quality due to its simplicity of work. After we add our dataset, in our dataset, low smooth null spectrogram, CNN of the unit types was chosen for implementation, and the idea is to, at the very beginning, increase the resolution of the input data by 2 times, and then, using the unit architecture, restore the quality of the null spectrogram. The encoder was ResNet 34, which was cut off at the end of 2 layers, since they are not suitable for our task. Decoder is created dynamically. The extra A block, can you see? The extra block at the end is needed to get the target's resolution, since after passing through the unit, the output resolution may not match the target. Extra block makes it an additional upsample and interpolates the resulting resolution to the target's resolution. Research pipeline. First, we need to get 2 different sets of null spectrograms. The first one we get with the help of Griffin Lim, which artificially smooth them. We will get the second set by applying super resolution to the smoothed null spectrograms. The next step will be to receive an audio signal using vocoders for further evaluation. We will have 3 sets for audio signals: original, cursed, and predicted. It's a green rectangle on the screen. After that, we can apply the mean opinion score metric to them and analyze how well our super resolution model improves naturalness of speech. The research is not yet fully completed, so I cannot show the results at this time. Thanks for attention. Any question?
What are the results? What are the results? Have you generated spectrograms? How many? How many?
I can't understand the question.
How many spectrograms you already generated by this pipeline? Сколько спектрограмм сгенерировано?
I use Russian dataset for speech to text, which called OpenST, and I use this audiobooks, which contains about 100,000 files.
So what is one like a sample of spectrogram? How it looks like? How many pixels How many seconds in one spectrogram you have? If it's from OpenSTT or LJ?
We speak about all pipeline or about super resolution?
First, you need to have some prepared data set. I'm asking about whether the data set is prepared. How many files, how many objects to train on you have?
For super resolution?
For whole pipeline. You need to generate first original MEL spectrogram, then Griffin-Lin spectrogram, then predicted spectrogram. How many of, like, describe your results? You designed a pipeline, so what you processed on your pipeline? How many files, how many objects?
I have not with files, haven't with files, because I, for training super resolution training now, I create a dataset from LJ speech, and I pre-processing audio include in transform of dataset for super resolution. What can you see screen with pre-processing? First five objects on the screen I include in transform dataset for super resolution. For Russian dataset, I don't implement yet this transformation.
Okay, I understand. Other questions? Thanks for answering questions. And that was our final presentation for today. I see that Said Mohammed not appeared. So any suggestions, maybe remarks on today's seminar, do you have? No one have. So thank you for participants. See you next time. That the next time will be the seminar one day before your second year students pre-defense. So try to prepare your presentations. I will try to give you valuable feedback to prepare the best presentation on your pre-defense. Please take my notes. Don't take it too close to your heart, but try to improve your presentations before pre-defense. See you next time. Goodbye.
Thank you. Bye.
Goodbye.
Bye.
Bye. Thank you.
Goodbye.